Hello, my name is Shir Peleg, and this is a talk about lower bounds on stabilizer rank. This is based on a joint work with Amir, Shpilka, and Lee Volk. One of the most interesting open problems in theoretical computer science now and then is the question of, are quantum computers more powerful than classical computers? And the widely believed answer is that yes, quantum gives more computational power to computers. And we have some evidence that support this assumption. So the first is Shor's algorithm that factors number using quantum computers efficiently, which is the thing that we do not know how to do in classical computers efficiently. This is due to Shor in 1997. We have Oracle and black box separations between quantum computers and classical computers. Some examples are Simon 97, Bernstein Vazarani from 1997, and Raz Tal from 2019. We have quantum computers have advantage in sampling problems due to Aronson and Arkhipov in 2013. And we have some separation for low depth circuits. For example, due to Bravi, Gosset, and Koenig from 2018, and Wath, Kotari, Schiffer, and Tal from 2019. This means that there are problems that low-depth quantum circuits can solve, but low-depth classical circuits cannot solve. But we also know that P is a subset of BQP, which is contained in P space. So because we do not know how to separate P from P space, we do not believe that unconditional separation is feasible in the near future, and it seems quite difficult to prove. So what can we do in the meantime? We have some techniques that shows a simulation of quantum computers using classical computers. So can we prove that these specific simulation techniques do not work? That means that there are some quantum computation that they cannot simulate efficiently. So this is the main questions that we are interested in here. So just a bit of notation, qubits are unit vectors of dimension 2 over the complex field. These are the notations. These are called pure qubits. And a state of the system is just a tensor product of n qubits, so it's a vector of dimension 2 to the n over the complex field. The law of the universe says that we can apply any unitary linear transformation and then measure. So this is a circuit, it gets its n qubits as input, applies some unitary operation, and finally it measures. So as I mentioned, the law of the universe says that we can apply any unitary transformation. But if we want to bound the fan-in of our gates, we can allow all unitary transformation on up to 2 qubits. So this is a standard gate set. And there is a fact that there is a finite universal gate set that can approximate every general quantum computation on up to 2 qubits. It uses unitary operation on up to 2 qubits, and this finite universal gate set consists of the following 4 metrics. So they are denoted, the first 3 are denoted C note, H, and S, and they generate a group that is called the Clifford groups, and these are what we call Clifford gates. And the fourth one is T, or the pi over 8th gate, and this gate is not in the Clifford group. A fact by Zhuo, Liang, and Chuang from the 2000s says that the T gates can be pushed to the inputs. This is very similar to how we push negation to the input when we deal with classical circuits. So here, if you have circuits of size S that use both Clifford and T gates and get n qubits as input, you can replace it with a quantum circuit that uses only Clifford gates, and its size is polynomial in S, but as inputs, it gets all the n qubit as the previous circuit, but also an ample supply of a magic state we call H. H is essentially applying the matrix T over the 0 qubit, and then applying some Clifford operation. So this magic state is if you get an ample supply of it, you can compute any any quantum computation. And this magic state is, as written here, cosine pi over a times the 0 qubit plus sine pi over a times the 1 qubit. So this is what we call the magic state. It's a fixed state, and we will use this name. A theorem by Gottesman and Knill said that Clifford circuits on classical input can be efficiently simulated using classical computer. This is true due to the fact that the state of the circuit is always a stabilizer state. And such state can be represented and updated efficiently using standard computations. So if we apply a Clifford operation on a stabilizer state, we can update it and store the relevant data using classical computing. Thus, a corollary that if the nth tensor power of the magic state can be represented as a small linear combination of stabilizer states, then every classical computer can be efficiently simulated. Because if that's so, we can compute polynomially many stabilizer states and apply the Clifford circuit on a stabilizer state, which we know that we can do and update, and just apply the linear combination before we measure. So this is an important corollary. This motivates the following definition of what we call a stabilizer rank. So for example, quantum state psi, we define chi of psi to be the minimal R such that psi can be represented as a linear combination of R stabilizer states, any R stabilizer states. And because we work with approximation a lot, we also need to define the approximate stabilizer rank. And by that, we denote it by chi delta of psi. And by that, we look at all the states that are contained in the L2 norm ball of radius delta around psi, and ask what is the minimal stabilizer rank of any state in the ball. And this is the approximated stabilizer rank of psi. So some known results or bounds on the stabilizer rank. We are mainly interested on bounding the stabilizer rank of the nth power of the magic states. So there is a lower bound of square root of n due to Bravi, Smith, and Smolin from 2016. There is an upper bound of 2 to the alpha n, where alpha is log 3/4 due to Kasim, Parashian, Gosset from 2021. And this is the last result in the line of work that improves alpha, and this is the best known upper bound that we know of. We also know that the stabilizer rank of the nth tensor power of the magic state is super polynomial unless p equals np. This is due to Huang, Newman, and Segedi from 2020. We know that the stabilizer rank is indeed exponential, assuming the exponential time hypothesis, due to Morime Timaki from 2019 and HNS again. And we know that the stabilizer rank is exponential if the coefficients that we use in the linear combinations are small. So the stabilizer rank is the minimal R such that psi can be represented as a linear combination of R stabilizer states. So if the coefficients in the linear combination are small or bounded, we can prove that the stabilizer rank of this magic state that we are interested in is exponential, due to BSS in 2016 and Bravi-Gosset in 2016 as well. And this is follows from some correlation bounds between stabilizer states and the magic state. And in this work, we give a linear lower bound for the stabilizer rank of the magic state, the nth tensor power of the magic state, and we give a lower bound of square root of n over log n for the delta approximation stabilizer rank of the magic state. And this is true for any delta which is sufficiently small, smaller than some constant. And this is the first such lower bound. There is an equivalent definition for stabilizer states due to Dehine de Moore and Van den Ness, and they prove the following. So a quantum state psi is a stabilizer state if and only if psi has the following representation. So just to explain the notation, when we have a binary string x, we can define an associated quantum state by tensoring the basis qubits according to the values of the binary string. So wherever we see 0, we tensor with the 0 qubit, and wherever we see 1, we tensor with the 1 qubit. And this is equivalent to indexing the 2 to the n coordinates that we have in our vector space, each of them according to a binary string. So this is equivalent, and therefore this is a basis of C2 to the n. And a stabilizer state is a stabilizer state if its representation in this basis is the following. So it supports on only indexing corresponding to some affine subspaces of F2 to the n. So we allow the non-zero coefficients to be only vectors that are in some affine subspace A. And the coefficients themselves are of the form I to the L minus 1 to the Q, where L is a linear function over F2, and Q is a quadratic function over F2. So we have this special basis, which is just the standard basis, and we allow the support of our state to be some affine subspace, and the coefficient of each vector basis element is I to the L minus 1 to the Q, where L is a linear function over F2, and Q is a quadratic function over F2. So this is an equivalent representation for being a stabilizer state. And this is true up to normalization. And from now on, for the rest of the talk, I will forget about the I to the L coefficient, just to make the notations a bit simpler. So now we chose a special basis for the 2 to the n dimensional vector space over the complex field, and we now can move, instead of talking about states, we can talk about boolean function or function from F2 to the n to the complex field. And we do it as following. So for every state, we associate the boolean function. We write the state as a linear combination of our special field element, a special basis element, and the function in the gives in the value of x the coefficient of the corresponding vector in the linear combination. So it takes x and gives c of x. And a stabilizer function is a function that is defined in the following way. So we have the indicator function of some affine subspace, and we multiply it by minus 1 to the q, where q is a quadratic polynomial. Q of x, where q is a quadratic polynomial. So just to give an example, what is the Boolean function associated with the nth power of the magic states? So for every Boolean vector x, the result of the function only depends on the Hamming weight of x, and it is sine of pi over 8 to the power of the Hamming weight of x times cosine of pi over 8 to n minus the Hamming weight of x. And the stabilizer rank of a function is the minimal r, such that there are R subspaces and R quadratic polynomial, and F is a sum, a linear combination of the R stabilizer functions that are associated with those subspace and quadratic polynomials. So yeah, we want to ask how many stabilizer functions are in the what is the minimal R such that f of h can be represented as a sum of R stabilizer functions. Each stabilizer function is defined by an affine subspace and a quadratic polynomial. So a similar question that only uses Boolean analysis is the conjecture of the quadratic uncertainty principle. So in this question, we are the conjecture is that if you can represent the end function as the sum of S function, each of them is -1 to any quadratic polynomial, then you need at least exponential number of summits. So this is very similar to stabilizer rank, but we don't have these indicator functions of affine subspace. And indeed, the stabilizer rank of the end function is 1, is very small. This is because we can take an affine subspace to be just all 1 point. But and another fact is when we allow linear functions in the power and not quadratic polynomials, then this is exactly the Fourier transform. And then we know that the result is exponential because this is the Fourier transform. We know that the Fourier transform of n depends on exponentially many basis elements. And the best known lower bound for the quadratic uncertainty principle is n/2. And it is very interesting to prove superlinear lower bounds for any explicit function. And Williams in 2018 showed that for every k, there is an NP function that uses at least n to the k summands of this sort in its representation. So this is the best we know about the quadratic uncertainty principle. And the stabilizer rank is a more general notion. So I'll just give a 2-minute idea of the proof. So recall that we have this special function, f of h, fh, that is the following. And the only thing we need to notice about it is that whenever we take x and y that have different Hamming weights, the value of f of h on x and y are different, okay? Because the function only depends on the Hamming weight of the vector, but for each weight, the function is indeed different. And we want to ask what is the minimal R such that f of h has such a representation. And we prove the following claim. So any function f that has stabilizer rank of at least n at most n over 100, there are 2 vectors, x and y and z, with different Hamming weights, such that the function agree on both vectors, And this does not hold for our spatial function f of h. And this immediately means that the stabilizer rank of f of h is at least n over 100. And essentially what we prove that, as I mentioned, we can only look at the affine subspace and quadratic polynomial that define each stabilizer function in the combination. So if you have a collection of at most n over 100 subspaces and quadratic polynomial, there are 2 points of different Hamming weight that in each of them all the indicator functions of the affine subspace agree. So that means that for every subspace, either both y and z are in the subspace or they are both outside the affine subspace. And the quadratic polynomial also agree on them. And as the the function only depends on the value of the identicator functions and the quadratic polynomials, it means that the computation is the same on both y and z, and thus the functions must agree. So essentially, we just prove the following claims. If you have a small enough amount of affine subspace and quadratic polynomials, you can find 2 points of different Hamming weights on which all the identicator function agree and all the quadratic polynomials agree. And once we do this, we get the lower bound that we needed. So let me finish the talk by introducing some interesting open problems. So the first one is improve the lower bound. We gave a linear lower bound for the stabilizer rank of the nth tensor power of the magic state. But as we saw, as I mentioned earlier, under standard assumption, this measure should be exponential. So any improvement should be interesting. And there are 2 follow-up works due to Labiv and Lovitz and Stefan. They use different technique, but gained a similar lower bounds or the same lower bounds. Again, this question of stabilizer rank might be similar to the notion of a quadratic Fourier analysis and the question of the quadratic uncertainty principle. So improving the lower bound for that problem is a very interesting problem from a different direction, not the quantum world, but the Boolean analysis world. And there is a lot to be done in this direction also. And can we do this, the same thing as we did here for other simulation techniques for quantum circuits? So we used a specific simulation technique, then we try to prove that this won't work, and giving a large enough lower bound for the stabilizer rank will indeed prove that this simulation technique will not work for any quantum circuit, but there are some other simulation techniques for quantum circuits. So can we attack them in a similar manner? So can we prove that they won't work for general circuits? Thank you so much for listening, and I hope you enjoyed the talk.